All right, let's get started. So, couple of announcements. First, we had talked about this earlier, very early in the semester, about this whole discussion on cheating and using other people's code or submitting an assignment that is not your own work. Very unfortunately, I was hoping we've put that one to rest after we caught the first case very early in the semester. But unfortunately, that did not fix the problem. In fact, it seems like it's the same student who has been found doing something very similar yet again on another project. So sorry about wasting everyone's time on this. I do want to re-emphasize that we are running the cheating scripts. It's not that now that we are halfway through the semester, me and my TAs have forgotten the fact that we made a big deal out of it one day. It is still a big deal. We have actually found a case, and now that since it's for the same person and it's twice, it really makes life difficult for me, because usually the way it works with the university, for those of you who have had the fortune of not knowing how the system works, it's still useful for your information. First instance of scholastic dishonesty leads to a warning, but the second instance of scholastic dishonesty actually leads to expulsion from the university. There is just no turning back from that. So if you're written up once, they keep it in your record. If you're written up twice, you're out. You have to apply for admission again. We are actually so me and my TAs are going through that really unfortunate decision right now on whether we take that student and report him or her twice and actually change the path of their career at this point, or no. So first of all, for the student, I do want to give an opportunity to come and talk to me. If you know, and typically in my experience, you know yourself who you are. And in the second, the more broader message here is, please be extremely cautious of this. We are still running the cheating script every single assignment. The only reason you don't hear me talk about it is because I was happy that I would never have to talk about it again this semester, but unfortunately that privilege got taken away from me last week. So for the one student, please, if you can come find me or my TAs or email us, that would be great, because it's going to be looks like it's going to be a very serious situation here. And for the rest of you, please keep up the work of not doing anything fishy and be very careful, because we are running the cheating scripts all the time. That said, last time we actually went in depth with binary search trees. So first thing we did was talk about where the word binary, search, and tree, what do each one of those terms mean and where BST comes from. Then we actually spent some time talking about some algorithms that we actually wrote together, and the mechanism through which we wrote most of our algorithms. We just put them right here, if you may recall. We started from the min function, and then we wrote the max function. So what we did in all of these cases was we actually used a recursive methodology, which made it really simple. Again, 4 situations. Every time you're writing a recursive function, start thinking, I have a root node and I have 2 subtrees. I have a problem to solve. How would I solve it if I knew the answer to the left and the right subtree? And that's usually what gives you your decomposition. So for example, for count, one of you said it's going to be 1 plus the size of the left tree plus the size of the right tree. And that's basically all we need. And then for your termination conditions, remove one of them, make sure that you can handle that case, remove both of them, make sure you can handle that case, and get rid of everything you left off with a blank sheet and make sure you can handle that case. And that gives you about 90% of your binary search tree algorithms, and a very powerful way of writing it. We have all talked about recursion in the past, and this is actually one case where recursion is in fact a very natural and easy way of solving problems. At the same time, I did want to spend a little bit of time looking at iterative solutions to some of these problems as well. And this is a general rule of thumb, in case I didn't emphasize it earlier, that anything you can solve recursively, you can solve iteratively and vice versa. There is no hard and fast, this problem can only be solved recursively or iteratively. You can always take one solution and convert it into the other. So just as a quick, in fact, let's just spend a couple of seconds on the whiteboard on what, say, something like min is going to look like if we were doing it iteratively. And let's see if I can find a chalk that's longer than 5 millimeters. About 9 millimeters. Alright, so this is the tree that we were working with yesterday, or on Monday that is. The minimum for this tree we all agreed on is this guy right here. It's a leaf node, and the leftmost, the actual leftmost node that we can find in the tree. And the way we did it was we said, well, we know that if I'm sitting at the parent, let's look at our recursive solution. If there is a left subtree, then the minimum is going to be equal to the minimum of the left subtree, because the parent is guaranteed, never forget that, left child is less than parent is less than right child. I'm being a little sloppy, I just put P instead of parent to conserve my scarce chalk over here. So if I have my left child, if I know the minimum of my left child, that's going to be the minimum, because there's no way the parent can be greater than the left child's minimum. So that's what we used, and we said, well, if there's a left child, go find the left child, the minimum of the left child. Otherwise, if there is no left child, that means we are looking at the solution. So for instance, if the tree did look like this part does not exist, then the solution is the node that we are standing at right now. And those two basically give us our solution. So the question is, can we actually do something similar recursively, just to get another flavor? Yep. Thanks. Excellent. Yeah, he did do that. Especially with him wearing the suit today, that is the clapping itself. So starting out right here, and we want to get to this guy, basically. That's kind of the idea. So we're looking for the leftmost node which does not have a left child anymore. So what does that look like iteratively? It's actually surprising. The iterative algorithm is about equal amount of complexity. In fact, in this case, about the same number of lines of code. Because all we are really doing is we start at the root, and we say if there is a left child, go left. If the left child does not exist, just return where you're at right now. And just go ahead and just return the answer as is. So I took the liberty of getting some of these functions in place just so we could save time today, because there were several examples I wanted to share with you guys. And just quickly jumping in right here. So what this just turns into is a very simple while loop. You basically start with a pointer right here. You always have to check that the pointer itself is not 0, because there can be that there's nothing in the tree. That's what that first P is. And otherwise, you just keep checking that there is a P to the left. And if there is a P to the left, you can just do P is equal to P to the left. So I start right here. This is where my P is pointing to. It's clearly not null. Is there a P to the left? Yes. So P starts pointing over here and is no longer pointing over here. Is there a P to the left? Yes. P starts pointing over here. Is there a P to the left? Not anymore. Return P. So really, in a simple while loop starting over here, we go left, left, left. As soon as you find your leftmost node, you're done. So this is just another solution to the same problem. It's just a min function, except that it's actually written iteratively, and you can do both iterative or recursive solutions to your problems regarding the binary search tree. Any questions about this, the iterative portion? So everything that we did yesterday can actually be done iteratively as well. For example, count would work the same way. Start at the top. You have to start going all the way. One option is go all the way to the end, and then just keep counting the nodes. Just write a loop that actually goes. If you have a left child, go to the left child, count the nodes, and keep iterating with your P until you get the solution. Count is actually a great one to think about for a second. How would you do it actually iteratively? Because it's particularly painful to do it iteratively, because we have to go both sides. What made smallest or min the easiest, very easy was because we were only chasing one direction of the tree. So it was almost like chasing a linked list, right? It's an exact same algorithm as chasing a linked list. What we're really trying to do is finding the last node of a list that's going from here to here through the tree. Left, 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 left. As soon as we say next pointer is null, done. Same amount of code there. But when you actually need to chase both sides, for example, for something like count, iteratively go here, iteratively go here, you basically have to count, then keep track with multiple variables. I've already gone down this direction, come back this direction, count, come back this direction, come back over here, count again, count again, count again. Becomes quite complicated to keep track of the fact where you are in the tree right now and what are the nodes that you've already seen. Compare that to the recursive solution. It's as simple as writing something like smallest, because what's really going on is, so just quickly looking at our count solution right here. So this is what count looked like. If root is equal to 0, return 0, otherwise return 1 plus count of right and count of left. This simple code takes care of all of what you would have to do if you were doing this iteratively. So this is actually a great example of something that's incredibly simple if you do it recursively, and does actually make you think quite deeply if you want to do it iteratively, one node at a time, just going through and finding and just counting the numbers. Because and a tree is very natural in that if you do the same thing, let's say we were trying to count the nodes in a linked list, your iterative algorithm and your recursive algorithms have very similar complexity in terms of writing code. Because in iterative, you're saying, remember what we did was, when we said we have a linked list, and now that we have even more understanding of recursion, what is the decomposition for the size of a linked list? Let's just call this root for now. What's the decomposition? It's really just 1 plus length of root to the next. Right? That's all it's going to take to do the recursive length. What would it do to do it iteratively? Not a whole lot. Just a very simple while loop that would just say count, 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 and go through it. Very similar complexity in terms of writing code for recursion or iterative. Binary search tree, whole different beast. Trying to do this recursively and go down both sides all of a sudden requires you to start thinking about where exactly am I in the tree right now. You need more than one variables to keep track of where you are at a particular, which node are you at, and then track where have you already been and where have you not been yet.
Sorry, can you quickly explain the 1 plus length?
Oh, sure.
Thing?
Let's do that.
Just a little bit.
So just a simple linked list has the root pointer pointing to the first node. Now, and the function we are actually wanting to write is, let's say, called length. which takes in one argument, node star, oop, the entire thing is actually going to return an int. So let's just first start with the decomposition. In these cases, often easier to start with decomposition. So if I knew the length of the list that is starting from this point, and always remember that a linked list is starting over here because root is pointing right here. If I have a pointer to this node, I can say that this is a list that starts at this point and goes to the end. It's a list as in itself. It has all the properties of a linked list if you start over here. So what is the length of this entire list if I knew the length of this list right here? What would be the mathematical formula for that? 1 plus the length of everything from here. So your decomposition is really just return 1 plus length of root. And since it's a linked list, there's no child, so we call it next. And again, just similar way of thinking in terms of termination. Can we handle the absence of a list? Can we handle the fact when root is equal to 0? Can this function take care of that right now? So we need to go ahead and add that. If root is equal to 0, what would be the length if root is equal to 0? 0. So you just return 0. If root is equal to 0, return 0. Now, can I handle, remember the interesting cases about a linked list typically are no list, a list of size 1. Can we handle a list of size 1 with this formula right here, with this function? Yeah. We can, because list of size 1 would actually imply you actually come in here with root is not equal to 0. We'll get into the return, which will say 1 plus the length of root to the next. That would actually get us back up here, except this time root will actually be 0 because root to the next is 0. And hence we will get return 0, so we'll get 1 plus 0, and the final length will be returned as 1. Now, and just for brevity, always a good idea to do one more case. Can we handle length list of size 2? Yes, we can, because we already know that we can handle length of list of size 1. This is just 1 plus that, and this will be able to take care of it. So, answer your question? Yes. Now, since you already asked the question, let's actually do the other thing, which is, what is exactly the length if we were to do an iterative solution for this? So, I'm being a little sloppy here just so that we can get through this rather quickly. All I'm trying to make is a point, and I'm just going to say int count is equal to 0. And in here, I need to say count plus equal 1, and then return count. So what does that lead to? So we have a length. I said count is equal to 0, just a local variable. And then I said while root. So if root is 0, this while is going to fail right away. We will return count is equal to 0. So we can handle the no use, the case where there are no nodes around. If there's a single node around, is that going to work? Root's not going to be 0, so we will actually get in here. We will get count is equal to 1 because count will be added, 1 will be added to the count. And now root will become root to the next. Remember I'm talking about the case with a single node, so root's pointing right here. So count will be equal to 1, root will become 0 because root is equal to root to the next, which is 0. So next time around the while loop is going to fail because root is now 0. So we will actually return 1. So that use case seems like it's going to work. Let's do one more. Can I handle the use case of 2 nodes? So we start out with root being non-zero, which means the while loop's going to go. Root's going to start pointing over here, and count's going to be 1. And then we go back to the top again. Root is non-zero, so then root's going to start pointing to here, which is nothing. And count will become 2. Next time around, since root's pointing to 0, while loop's going to fail and we'll return 2. So make sense? So we basically have the recursive solution and the iterative solution written right next to each other. In terms of complexity and thought, not too different, very, very similar actually. Just one is doing it iteratively, the other one's doing it recursively. Where things become interesting is when you actually have to go 2 paths. That's where recursive becomes significantly easier to deal with. So this is one way of thinking about when does recursive solution become more interesting. In terms of a binary tree. So when we were chasing just one side of the tree, looking for the smallest, that's easy. The question is, can we do something like count iteratively on a binary tree? The answer, well, you can always do it, but it's actually a significantly more involved process that you basically have to apply, where you have to go through and keep track of values. You actually go down, maybe start here, go all the way to the left. Use the parent pointer to come back here, go down here, use the parent pointer to go back here, go back here, go back here. And you basically have to maybe even use some kind of breadcrumbs where you say, like you guys did in the maze, where you say, I've already visited and counted this node. Because something has to keep track of what has been visited versus what's not been visited. Almost blows my head off if I try to think about it in terms of how do you actually do this iteratively. Possible, clearly. But so this is where it's actually a great example of where recursion is a significantly more simpler, if you think in terms of count of a binary search tree, where recursion gave us a solution that did not require us to even think for more than 2 minutes and required 2 lines of code. We are talking about a very complex iterative algorithm and perhaps even adding more data to the node itself just for taking care of breadcrumbs, for just making sure what has been visited versus what hasn't been visited. So a good example, which is why when you will be working with binary search trees, almost all cases in my experience, recursive algorithms tend to be simpler to write. And if you can actually wrap your brain around it, it's usually the easiest solution to almost every problem that you'll see, for example, on an exam or a homework having to do with binary search trees. I have been surprised. One of the reasons I spent this time talking about the difference between the two is because I was quite surprised, especially during the summer, that I actually saw several solutions on the exam when students actually wrote iterative solutions, which made them extremely complex and barely anyone got full credit for the iterative solution that they wrote because they made one mistake or the other, they missed one detail or the other, where the problem could have been solved recursively with just 2 to 3 lines of code in most cases. So while you can solve it iteratively, it will make life easier in most cases to just do it recursively. And we've done 4 examples in class already of how you would do something recursively around this. And we will actually do a couple more before we leave today. Now that said, there was actually another iterative example or an important concept when we are dealing iteratives that we often use, and I just want to get to that. So I'll be pushing all of this code to SVN so you guys have some examples. There's no way I can get through all of this in class today. But there was actually this one where I did want to spend some time on, because when you are writing an iterative solution, or if for whatever reason you're hell-bent on writing an iterative solution, there is a very valuable function that will come in handy. In most questions on the exam, we will give you guys the successor function. So what a successor is it's kind of a generic function for binary trees. What successor really says is let's just see if I can remember what the values here were. So I think it was something like we were doing 1, 2, 3, 4, 5, 6, and 7. That's what our binary tree looked like yesterday. So if I actually give you a pointer right here, and I ask you what is the successor of this node, typically what the successor function is defined as is it's the next order in the ordering of things, in the ordering of values, where ordering means 1 is less than 2, is less than 3, is less than 4, is less than 5, is less than 6, is less than 7. If I actually ask you for a successor of 6, your answer should be 7, because 6 is the thing right after, 7 is the thing right after 6 in your binary tree. So this one's obviously easy. If I ask you for a 6, you just give me a 7, because you have a right subchart. Where things become interesting is, if I ask you for what is the successor of 4, what is the answer when I ask you for the successor of 4? So mathematically, we know what is the successor of 4 in this. So there's two options being floating. People are throwing back at me. There is the number 5 and the number 6. It's by definition, the successor is in the ordering the next thing that occurs right after the node you're currently pointing at. In the ordering, what's the thing right after 4? This is
6.
Yeah. Well, no. So it's not 6. So this is stuff you learned about when you were 3 years old. If you go 1, 2, 3, 4, the next thing that comes after 4 is a 5. So that's the successor. In the ordering, in numbers make it really easy. If it's a string or something else, it would be a little more complex. But what's important is that if I was to take this data and write this as a sorted list, what would come right after 4? That's the definition of successor. So what you're trying to look for is the value that comes right after the node that I'm currently pointing at. So we'll do a couple more examples just so I make sure that it's done solid. Yes?
So if there was no 5, it would be 6 though.
If 5 was not there, then yes, the successor is going to be 6. Is the thing, like I said, one of the easiest ways to think about it is, if I was to take all the data stored in my tree and write it in a sorted list, starting from here all the way to here, what will come right after 4? That's the successor. Yes.
Isn't that just the smallest value on the right side?
That's we'll get into the algorithm here in a second, but what you're giving is the solution, and you're right. So let's do a couple more examples. So there's a few situations here, and getting our 5 back into the picture. So there's really 3 situations here. What if we were looking for a successor of 7, which does not have a right child? What's the answer to that? If I'm looking for a successor for 7, the answer is a null. There's nothing there. So successor of 7, and we'll just call it S of 7. That's null. If we drop it right here, the successor is 7 right after this, which is quite obvious. What's a little more interesting is, what if we were looking for the successor of 5? What's the answer, first of all? Again, elementary school math. The answer is 6. How do I get from 5 to 6? Yeah, it needs to be its parent. So the interesting cases are 1, and we'll just have to write these down because it's a bit difficult to keep it all in your head. And this is what makes iterative algorithms a bit of a pain to deal with. So one situation is I have no right child, at which point the answer is a null. This is when there is no right child for a particular node. is that actually a complete, this is what we did for 7, but is that actually an accurate way of saying it?
No, there's 3.
There's 3 as well, exactly. So 3 does not actually have a right child. But what's the successor of 3? The successor of 3 is 4. So 3 needs to go back to its parent, needs to go back to its parent, and that's when the answer is going to get back to us. So but let's first keep track of all the use cases, all the different possibilities we're going to run into, and then we'll come up with algorithms to solve each one of them. Successor is actually a good exercise to kind of wrap your brain around the complexity of the tree and what it can actually entail. So no right child's one of them. We talked through that one. There is the situation where you have a right child. One of you already gave the answer for that one. When you have the right child, what is the successor?
The minimum of the
Minimum of the right child. And then we look at this number 5. Also, there is no right child, but the parent itself is the answer. So let's rehash this piece of information. We know how to deal with the case when there is a right child. That is easy. That's the easy case. The second situation is there is no right child. When there is no right child, there is 3 and there is 5 as 2 interesting examples. When there is 5, the answer was the parent itself. How can we detect this use case? What exactly happened? Why did 6 become the answer but 2 not become the answer for 3?
5 is on the left of 6.
Because 5 is on the left of 6. Since 5 is on the left, 5 is actually the left child of 6. If you have a parent and you are the left child of your parent, then your parent is the successor. That's basically what it comes down to. Because you don't have a right child, that means you are the smallest value in the left subtree. Your parent, in fact, there is no other value in the subtree that can be smaller than you. That means your parent is the next biggest value. If you go to the parent and you find that you are the left child, then just simply the answer is the parent itself. So that was the relatively easy case again, when there's no right child, and I guess I'm just going to use first person. So I am a left child. If you are a left child, if your node, the node that we are on is a left child and does not have a right child, again the answer is easy. It's the parent itself. So those 2 use cases are relatively easy to deal with. The third one's kind of a painful one where we are dealing with, so for example, let's apply one more case. If we were to look for a successor of 1, do we know how to solve that one at this point? So 1 falls in case number 2. No right child, has a parent, is the left child of the parent, problem solved. The third case is when there is no right child and you are the right child of your parent, which is, in our case, the value 3 right here. So what does 3 need to do? It needs to go back to its parent. Now, all we know is right now that what we're really looking for is, we do know that 3 is actually the largest value in this subtree, the one with the parent in it. What we are really looking for is the parent right here, which essentially is, if this is the largest value if 3 is the largest value in our subtree, then the parent of this entire subtree is guaranteed to be the successor of the rightmost node in here. I know it's a bit of a mouthful, but so I'll just repeat it one more time. If we know the largest if we know that what we are dealing with is the largest value in this subtree, then the parent of that subtree is the actual successor. So this one's a particularly simple use case where I have 3. My parent's not my successor, but my parent's parent is my successor. But there is actually another painful case here, which is, say, the number 7. If we actually started at 7 instead of starting at 3 this time. Because in case of 7, I have 7, I have my parent as 6. I know that 6 is not a successor because 6 is, I'm a right child. But then, even my parent is a right child. And since my parent is a right child, even that is not a successor. So 4 is not a successor of 7, and then 4 needs to go to its parent to see if it's a left child or not. And if it's and in case of 4, there is no parent, so the loop terminates saying 7 does not have a successor in the tree. So the third one's the painful one again, like I said. What you basically have to do is, I go to my parent, until I get to a node which is a left child of another node. It's a simple while loop, and actually a very interesting example where iterative does work a little better if you're actually trying to do this, which is why successor is kind of the foundation of iterative algorithms around the binary tree. You start at the node, you go to the parent and you check if the parent, is a left child. If it is, then, so I start here, and in fact it's becoming kind of clumsy to use the word parent and child. I start with P pointing to right here. Is this guy a left child? No. P starts pointing right here. Is this guy a left child? Yes. That means this is my answer. The first time I run into a node which is a left child of its parent, that's going to be the answer for successor. So if we translate that into code, this is kind of what it begins to look like. So if you have a right child, then you just return the smallest of the right child. That's our first case. Easy. Else, you actually have to start that iterative loop, and you keep checking so how do I check if I'm a left child? That condition is important to kind of nail down from as soon as we start. How do I know if I'm the left child of my parent? If I'm at a node P, and I want to check if I'm a left child or a right child, how do I do that?
If parent P's parent.
So what I have to check is P to the parent. Yeah, sorry, go ahead.
And that one's left chart of that.
So P to the parent to the left is equal to P. That's really the condition that you need to check for, right? So in this case, we have P and then we have P to the parent. So that's basically the same as P is really being set to P to the parent. So that condition is being checked. The other condition is being checked is that if there is indeed a parent, because if there is no parent, if we are at the top, then we want to just return the null. And then what we are really going to do is keep doing that loop. So you start at a particular node, and you keep going up and up and up. Basically, P to the parent, and that's what's happening over here. You keep going to the next node up and up the stack until you come across a node which is either a left child of something or it does not have a parent. If it does not have a parent, you want to say there are no successors. If it does have a parent, and that parent is and it's the left child, then that parent is your answer. So I start at 3, I go to my parent 2. 2 is in fact a left child, so 4 is going to be the answer, and that's what gives me the successor. Again, it is a bit of a mouthful. It might require you to think about it a little more in your free time. But the algorithm is, in fact, rather simple, where you can actually write a successor where you can start with a node and keep going up until you discover something that's the left child of its parent. If you are the left child of your parent, in case of 5, then the answer is immediate. The iteration terminates the very first time itself. Like in case of 5, you look for your parent and this case will pass saying that I am the left child, hence 6 is going to be the answer. Parent's going to be the answer. So why am I taking you through the successor is probably more interesting. Once you have the successor, it's actually quite valuable because now you can actually start writing more useful iterative algorithms. Remember we were talking about how it's going to be a real pain to write the iterative algorithms? So having the successor function available to you does actually make writing iterative algorithms a lot simpler with a binary tree. Because now you can really iterate through the tree. If I have a pointer to 1, my smallest node, I can just simply say, give me the successor of 1 and it'll give me 2. Give me a successor of 2. Now can we write count quickly using the successor? Much simpler than the way we were thinking about it earlier, which was kind of driving us crazy. Because if I want to write count using the successor, it's significantly simpler. Actually, you know what? I'm just going to type it because it's going to be faster and it'll leave you guys a trail to look at later. So if I want to write a count using the successor function, let's put it all the way at the bottom again. So what is it actually going to look like? You have the root. The first thing we can actually do is just count. Just get a pointer to the smallest node. 1 right here. There's a couple of ways to doing that. I'm actually going to take a bit of a shortcut. So just like there is a function called successor. Successor is the thing that actually is right after you. There is an equivalent function called predecessor that is often defined and used with binary trees. What does the predecessor do? It gives you the value right before. So what will be the predecessor of 4?
3.
What will be the predecessor of 3?
2.
It has a very similar algorithm that actually works exact opposite. So what we need to do is we are actually going to start at the root and keep calling predecessor until we actually get to this value. And then we're going to go back at the root again and just keep calling successor until we get to this value. Yeah.
Wouldn't it be easier to just to get the smallest element in your binary search tree and then just call the successor?
That's definitely one way of doing it. So the one quick difference is that we need a function for smallest. The current function that we have for smallest is, in fact, let me quickly check. I believe it actually will work. You're right. The function called smallest does actually return a node pointer, right? It's not in my head anymore. A recursive copy. Just give me 1 sec. Yeah, so you're right. So we could just so there's one option, and let's actually go with that one since that one's a little more intuitive. Let's actually call smallest of root node star so this gives us the smallest pointer to this value right here. And then from here on, we can basically just do while successor of min. Because remember, the successor will keep coming until you reach the highest value, at which point you'll get the value null back. And we can really do while min is equal to successor of min. And simply just do count plus equal 1. So we need to define a variable called count here. And then we'll just return count. So you keep going, min is equal to successor. So you start with 1, then your pointer is going to, you're going to get a pointer to 2, a pointer to 3, a pointer to 4, a pointer to 5, 6, 7. And this will just count all the nodes through. Yeah.
Shouldn't count be 1?
When we actually start out.
Yeah.
So smallest. So count is equal to 1, minimum successor. Yeah, you're right, actually, thanks. It won't be 1, actually. So here's why it can't be 1. If we actually, so let's start with that. If we actually set count to 1, what does that imply? There's one case that we can no longer handle. If there is no nodes in the tree, then we cannot handle that. So what I'm really missing is I'm actually overcounting or undercounting 1. So let me actually get rid of this ugliness. That's the real answer. This is what I really needed to do. So now if there is no tree whatsoever, there is no smallest value, then this is going to fall through and we'll return count is equal to 0, right? If there is indeed a min, then that means there is at least one node, so you'll get a count is equal to 1, and then it will look for its successor. If there is no successor, then we'll break with count is equal to 1. If there is a successor, then we'll do count 1, and this while loop will continue to run. Make sense? So that's kind of the idea behind successor, and that's why it's kind of at the foundation of writing iterative algorithms. Really makes life simpler. When you're dealing with iterative algorithms in case of a binary tree. Some other useful functions, by the way, that are worth thinking about.
Can I ask a question?
Yeah, please go for it. Sorry.
Before you make that change that you took the mean equal to successor mean inside the while loop,
Mm-hmm.
before that, so it would, before it run into the while loop, it would set the mean equal to the successor mean,
Yeah,
and then check the condition?
that's right. It was actually it was getting checked, and in fact, more importantly, I think I'll make a slightly bigger statement rather than answering your question. But I had there, and when I use the word, I should get rid of this ugliness. I actually was saying it the right way. It was really just ugly code, because at the least there is a confusion whether that will happen first or the other one will happen first. Exactly why we are talking about this. A perfect example of bad code when the code reader cannot look at the code and understand what the code is really trying to do, because there is a confusion. You can interpret it this way or that way. Can we find the answer? Yes, we can if you open up your C language manual and understand how C++ does the precedence on the equal operator. Do we want to be doing that? Do we want people to actually be doing that? Typically, no, when there is actually a much cleaner way of doing it, which does not have that ambiguity anymore. So while, yes, we can find the answer to that precise question more than one ways, either opening the manual or just seeing if this works or not. Anytime in doubt, it's actually better to go with the cleaner code that actually just is very clear what it's really doing. Because if you are having a confusion writing the code which way it's going to work, almost always the reader is going to have the same confusion reading your code how it's really going to work. Does it make sense? This actually, I'm just going to use an example from something Professor Pratt always talks about. For those of you who have been in his class or have read his textbook, he's actually a very accomplished writer. He has a very good command of the language. And one of his rules, if you read his 10 commandments of writing on his website, he actually talks about, he carries like a pocket dictionary with about the most common 2,000 or so words in the language, a very small dictionary. And if there is a word that he's typing and he does not know the spellings for, he looks up in that dictionary. And if he cannot find the word in the dictionary, what does he do? He doesn't use that word, he uses a different word. Because if he's having confusion figuring out what that word means and what is the exact way of using it, then the reader is also going to have the same problem when they're going to try to read it. So why put your readers through that pain? Why not say it a different way? Same applies to your code. If you're having confusion, how is this really going to run? It's probably a better idea to just do it a different way where you don't have a confusion, because your readers are going to have the same confusion in the future. So just a general good use case to context to remember. So the other one I actually wanted to write was, there's a lot of things around how do you actually print a tree. And again, I think we'll do a recursive solution and an iterative solution for print. To kind of finish this off. So if I want to print, so print, and notice that a word I used is print ordered. So print ordered would really mean I want this printed as 1, 2, 3, 4, 5, 6, 7. I want it printed in the right order. Do we know how to do that with a successor? In fact, really, really well, because we'll basically do the exact same thing. Okay, so I can't seem to figure out how Windows works, so I'm just going to use the same thing again. And then we can just do while min is equal to successor of min. And then for each node, we are simply just going to do printf. In this case, since it's an integer tree, we can just do printf, and really just we have at a given point in time we have the node, and we just go node to the value. So you print the value, you print the space, then you move to the next one, then you move to the next one, and just to kind of top it all off, what I'm going to do is just add a new line at the end. So this is what this code will do, is it will go to the smallest, which is 1, then print that, then find the successor, which will be 2, then print that, then find the successor, which will be 3, print that, and so on and so forth. So you'll actually get an ordered list of everything printed. Now let's actually try to do the same thing with as a recursive algorithm. So this one's a bit interesting. How is the recursive solution going to work? We want to print things in ordered fashion. So how is the recursive solution going to work? Anyone has any suggestions?
Call the website.
What's that?
Call the website.
So
and
let's
then call the
spend
website.
some time thinking about this, maybe right here. So let's start with a very simple tree. You want to print the left side. Somebody was saying that. Print the left tree, the left subtree. Then what?
Call the right side.
Then call the right side.
Oh, no.
You missed something very important there. Print the actual parent, and then print the right side. Will that take care of it? Actually will. So and then let's make sure we take care of our other cases. What is the other termination conditions on this? So we'll try the method that I was talking about earlier rather than going some ad hoc ordering. So we now know how to deal with this situation. Will our solution work for this situation if there is no left child?
If it's no, just not to.
We'll have to put like the if root is equal to 0, print nothing. If we had the termination condition, will this work? And will this work? And will this work? So that's pretty much it. So the recursive solution is going to look something like if root is equal to 0, then basically you just return print nothing. Else you print root what's going on? root to the left. Then you have printf, %d space, maybe again the same way, and then root to the value, and then otherwise print root to the right. And just for brevity, I'm just going to add a return there. Should this work from printing the ordered tree? And that is actually true. That's all you really have to do. Remember to print the left first, yourself, middle, thing to the right, and this will give us an ordered printing, and it will actually handle the cases where some subtrees don't exist. Yeah.
When you call print, would it go to the iterative solution or the recursive solution, since they're both like named the same thing and both take root?
So that's a great question, and that's a great C++ question in language. There's actually other things over here too which are not going to compile the way it is. So the first answer is the compiler is actually going to complain because there is really no difference between the two, which means the compiler will not be able to tell which ones to run. And when it cannot run, it's not going to try to second guess it. It's just going to ask you. Just one more thing I wanted to do quickly. There's actually another kind of printing that we sometimes do, and it's a useful thing to think about. So in binary trees, there's a couple of properties that we haven't really talked about. When we talk about binary trees, we've talked about count, which is the total number of nodes. There's another very important property of the tree, which is the height of the binary tree. The height of the binary tree is 1, 2, 3 in this case. That's how tall my tree really is. And there's actually some interesting mathematical properties that come with height that are worth noting. So if I have a tree of size 1, and we're just going to do a few elementary examples here quickly. So if I have a tree with a single node, the size is 1 and the height is 1. I have a tree with 3 nodes. The size is, let's call it count, since that's the word we've been using so far. The count is 3, but the height is actually 2 for a tree like this. For a tree that's on the other side, the size or the count is 7, the height is 3. Anyone see a pattern that's emerging here? What is the typical height of the tree given its count?
Log base 2 number of count.
It's log base 2 of count. That's typically how we calculate height, is log base 2 of count. What is the assumption that this formula is making though?
Each parent has 2 children.
Each parent has 2 children.
It's balanced.
It's balanced, exactly. That's the assumption. Because if I could have a tree of size 3 that looks like this, and now the height is 3 and the size is also 3. So this is the best case. The worst case is that the height is count itself. So the height is really somewhere between count and log 2 of count. Worst case, best case. How long, now from going back to something that we've talked about in the past, how long does it actually take to search something? Or do any of the algorithms that we have talked about on the tree? Most algorithms on the binary tree, for example, if you're trying to do a search, like if I'm trying to do a search on the number 3 in that tree, how many hops it's actually going to take? I start up here and I want to get down to 3. How many hops is it going to take? Really, it's equal to height minus 1. Remember, the height is 3. If I had a bigger tree, it'll be more hops that it's going to take. So what tends to happen is that the big O of a typical search, for example, let's talk about search quickly, is typically really just equivalent to what the height looks like. And oftentimes you will hear people talk about binary trees as they're log of n. So this is kind of an important thing to remember. People will talk about binary trees as a log of n data structure. Where does the log come from? They're really assuming that height is log of n, and they're assuming that the algorithm, which is typically what you do on a binary tree, is a search, is actually going to take just the same number of hops as the height, which is, the second one's an accurate statement. The first one is actually an assumption that the tree is balanced. If the tree is balanced, it's a log of n data structure. If the tree is not balanced, it's an O of n data structure. And really kind of falls somewhere in between. So that's an important terminology to remember. One, the fact that it's a logarithmic data structure. Two, the fact that there is this thing called height, which can be anywhere between n and log of n. So that's something to take away from this. The other thing to take away is that we also have another concept called levels in a binary tree. So a level really is, this is level 0. You start at the top and you count towards the bottom. Level 0, level 1, level 2, level 3, if there was another one, level 4, and so on and so forth. So that's something that so while I actually won't give you the answer for this, there is actually another kind of tree printing that we sometimes do. It's called level ordered printing. The idea is that you, rather than printing 1, 2, 3, 4, 5, 6, 7, a fully ordered printing, we may specify just print everything in level 1. And you have to figure out how to print everything in level 1. So it's kind of like a search, a depth search. I won't actually give you the answer because it actually is pretty simple if you think about it. So it's kind of an exercise left for the user. Just think about it. If you have any questions, ask the TAs, or Friday my TAs can go over the solution with you guys. What I do want to finish off before we walk out of here today is the actual search, since at the end of the day this is called a binary search tree and we've talked about everything in the world except search. So let's actually talk about that. The reason we didn't do that is in fact because search is the simplest of all of these algorithms. It's actually simpler than everything that we have done so far. Because what does search look like? If I want to do a search in this recursively, what is the search actually going to look like? So if, again, let's do that, our strategy of how we actually generate these recursive algorithms. So let's not add mark about it. We have a binary tree with a left child and a right child. What do I really want to do if I want to search for a value? First of all, do I need to search both sides? So if I'm searching for, say, the number 5 and my root node is 4, which side do I want to search? Search only the right side. So if I have a tree that looks like this, the value that I'm searching for, I should compare that value with my current node, the root that I'm at. Depending on if it's the value I'm searching for is, if it's equal, that means we are done. That's the search done. If it's 5 is greater than 4, that means I want to look in the right child. If the value that I'm looking for was less than 4, say the value was 3, that means I want to search in the left child. Make sense? And so really enough said in terms of all we have to do is just write a simple search function here. It can return the pointer to the node which actually has the value, otherwise it'll return null. And it's important to notice that this is going to take another parameter, say called value, which is the value that we're actually going to search for, because otherwise the search function won't make a lot of sense. So that said, we're going to do the same thing here. If root is equal to 0, return 0, because I want to return a null pointer. If root to the value is equal to value, return root, right? If root to the value is greater than value, which way do I want to go? So if root, so let's nail this one down. If root to the value is greater than a value that I'm looking for, that means I actually have to look this way, because that means I'm looking for 3, say, in this. So I'll have to be looking at the left child. So go root to the left. If root to the value is less than value, return search root to the right. And that's pretty much it. That's your entire search function. Because at any given point in time, if I've ended up on a node which doesn't exist, like something like this, it's just going to return a null. If at any given point in time I have actually found my value, then I'm going to return a pointer to the root. Otherwise, I'm just going to search in the left child and return whatever I get for the answer, or search the left child and return whatever I get for the answer.
So if we
But
didn't find that value, we're just gonna return 0.
we're going to return 0. That's because we are basically returning a node pointer. Remember, pointers, always remember that pointers, 0 is not a valid pointer value. So you can exploit that to your advantage and return a 0 when something is not found. So we are just going to return a null pointer, essentially. There is actually a mistake I'm making here, by the way. What's the mistake? I'm not passing in value. Yep. And that gives us our search solution. And now we have basically a solution. So we've done print level, leaving it as an exercise for you guys to do between now and Friday. We've done min, we've done max, we have done recursive, we have done iterative, we have done successor. And there's a few other example functions that I have in here that I'll push for you to just take a look at for other examples. The 2 most important ones are insert and delete. How does an insert or delete work? These are by no means efficient inserts or deletes, but they are just useful to have an example of on how does a binary search tree actually get constructed over time. So that pretty much is everything I wanted to talk about binary search trees in this class. So any questions? Yeah.
Is predecessor recursive or iterative?
So predecessor, I mean, again, you can write it whichever way you want.
Which way?
Iterative would be the cleaner. It's very similar to the algorithm that we did for the successor. The only difference is, so since we have 5 minutes, let's deep dive into, we talked about the function successor, and we looked at the code as well. I want to spend a moment, given the question, talking about what does the predecessor look like if we were to write the predecessor function. So what is the predecessor of, say, 7? It's parent, and 7 is a right child. Right? What is the predecessor of 5?
4.
Parent, but it's not a right child. Parent, but is a right child. 4 becomes your answer. Predecessor of 3, parent, and I'm a right child, done. Predecessor of 1 does not exist. Look for the parent, doesn't have a parent, the answer is going to come out to be 1. So if you take the successor function and simply replace that condition with from left child to right child, you keep following the parent until you get into something that's a right child of its parent, you basically have your predecessor. So it's actually a very, very simple algorithm with just literally one change. Instead of left, you actually do the right. In most cases on the exams, when we ask you to write algorithms for binary search tree, either we will say write a recursive function and not give you the option of iterative. If we give you the option for iterative, we would typically give you, specifically say that you can use successor and predecessor, and even smallest and things like that, so that you don't have to write all these functions yourself. Because otherwise, iterative is a real pain to manage all by yourself. So that's basically it. And I think there's just one more concept, and this is just C++ that I wanted to talk about quickly. I was surprised that none of you pushed back on what the hell is the static doing over here. What is that supposed to mean?
It can run without.
No, it keeps the values constant even when you.
So that's the definition when you use static for value. This is a function that is being declared as static.
It can run without declaring.
So what static does to a member function, again, the buzzword is member function here. When you declare a member function to be static, it basically implies that there is no this pointer passed into this. So literally, and we can try this out right now if you want to play with this. There is no this pointer. We are not getting anything out of this. And that's because this function is static, and the compiler has already said this is not a declared variable. So when you declare a member function as static, you no longer get a this function.
What's the advantage of using static?
And that's a great next question, which is what's the point of having something which is a member function but does not have a this? So the advantage is that you can actually call successor without actually having to have a specific object be used with it. So for example, successor is actually a part of the struct BST. I can actually call successor by just typing BST : successor and just pointing a node function. I do not have to do one of those a.successor. For non-static member functions, that's the only way you can call those functions, is by associating them to a specific object by either using the dot operator or using the arrow operator, depending on if it's a pointer or an object. If you want to have the ability to call that function without having to associate with an object, because you don't care, and when is this useful? Because you don't care about what your data members are at this point. If you don't need access to your data members, that means you don't care if it's associated with an object or not. At that point, you can just declare it's static, and you can just call it by its full name. Again, full name is critical. You cannot just say successor, compiler is going to bounce back at you. But if you say BST : successor, you can just call this function. It does not have to have a variable of type BST used with it. So it's basically a way of, so to talk about what is the advantage of doing this, it's basically a way of taking functions, even if they are not using data members, but are just related to that other function in that struct. You can just call it static and just put it inside the struct. So it all stays in one place. Can be called using a BST : syntax. That way, it's very clear that it is the successor function when inside the BST struct. But you also have the benefit of a non-member function, which is you don't always have to call it with an object with a dot notation or an arrow notation. Does that answer your question?
So a function like printf is a static function?
A function like printf. So printf is basically a global function. Why is that? So printf is not a static member function because you don't have to use a : before. But the properties that BST : successor and printf have are very similar. You're absolutely right, because just like you can call printf without doing an a dot on it, you can now call BST successor without doing an a dot on it. The only difference between these two at this point is that when you call successor, you can't just call successor, you have to call BST : successor. But otherwise, this is just like any other C function that you would have written in C. Not necessarily. It's not really a member function, but it's written as a part of the struct just for cleanliness. So it's a useful thing to have, particularly when we are dealing with binary search trees. It's actually a very useful thing to actually play with. Exactly why I have it in the code example, so you guys can play with it a little. All right. Any other questions? All right. So we'll pick up on Monday.
Can you have a static on an operator override?
On a static on an operator override? That's actually a good question. No, that wouldn't make sense. Yeah, that would not make sense. So that would be the same as writing so you can do operator overrides that are non-members, and that would be the exact same thing as writing an operator as a non-member.
But see out and see in, they are static functions, aren't they? Because you have to use ST.
No, C out and C in are operators actually, they are not functions. C out and C in, so that was related to his question. Because C out is really,
It needs to be equal like STD.
oh no, so that's a whole different concept actually. That is, it's another concept in C++ called namespaces.
Oh, yeah.
What you put std is the namespace.
Okay.
So this is not exactly the same, this is a static function, that's a namespace. Namespace is declared, it's a different syntax when you declare it. But it's your observation is right, they both are called exactly the same way. We could have created a namespace called BST and put everything in there and then called it from there, that would have worked too. But they're really fundamentally different though. Namespace is purely for naming, this one is basically making it kind of a memory function by putting it inside of BST.
So I'm in the Naval ROTC here, and in the middle of the semester we have to kind of get like a snapshot of our grades.
Okay.
So if you'd be able to just sign off on like what I kind of had as a grade right now, it doesn't have
Sure,
to
can
be
you tell me what your exam looked like?
Yeah, I got a 36.75.
Okay, that's a pretty strong. I don't need to know much else.
Thanks, sir.
Sure thing.
Have a good day.
So if you're doing operator overloading and you write a member function for that, and then say if you write another member function after that, and you use the operator that you overloaded with the correct parameter, would it use the overloaded operator?
So the overloaded operator, so yes, if you use it with the correct parameters, then it will use the overloaded operator. Because again, the way the compiler thinks is A plus B. It sees the A followed by a plus sign. It's going to say, what is the type of A? Does A have an operator overloaded for plus? If the answer is a yes, then it's just going to make sure that the argument on the other side is kosher. If it is, it's just going to leave. So the ordering in which you define doesn't really matter.
So once you define that operator overloading,
Anywhere else you actually use that type with that symbol, and the other side is the correct argument, you will get the correct answer.
and then in one of the other functions in the project that's due today, I saw this one syntax and it was return something is less than this. Does that automatically turn into a Boolean value?
That's right. Yeah, it turns into a Boolean
So
value.
that's just like a C++ thing?
No, it's there in C as well.
Oh, really?
Yeah, it's just a generic thing. Generally not a big fan of that syntax, but because of the exact reason that you just are here for, right? That there's this is an example of code that is not crisp clear. You have to think about what it really does. But yeah, I actually can't recall how it's done in the assignment, but the way I would say, at least you want to do it is, and it might be this way. If you put parentheses around it, in my view, that becomes a little clearer. At least it says what it really means. So if you have something like return A is less than B, then you kind of know that the parentheses will make it clear. So that's a better way of writing it. You can just write return A less than B, and that also works. That does actually confuse me a little, always, because it's not clear exactly what it is. So I typically, when I do it myself, I would put parentheses. Now I'd have to look at the code and see if it's using the parentheses or not. It wasn't? Yeah, so personally I prefer this syntax. This is slightly better. 2 extra characters, but increases the clarity of what it would mean.
And last question when I was doing the operator overloading, to account for the fact that you had to copy everything over into the new array that you made, like if they're...
So you're not talking about operator overloading, then you're talking about question backs, basically? Or the amortized doubling?
Yeah, that was part of the operator overloading.
Gotcha, okay. So tell me more. Maybe I'm missing something.
You